Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Interview questions in chemical engineering. Heat transfer part 3. I would appreciate if you subscribe to the channel. It will motivate us to produce more free knowledgeable content for you. So subscribe before you forget. For every question, you are given 20 seconds to think about your answer. Then the answer will appear. Check your answer is correct. You will have 4 questions in this video with answers. We will move on to the questions now. In the last video on heat transfer part 2, we finished with question number 10. So we will start with question number 11. Question number 11. What is draft in a furnace and why is it required? How is it measured? And how is it controlled in the furnace? Your time starts now. Your time is up. The answer. Draft is defined as negative pressure at any point inside a fired heater or a furnace. Furnace draft is created in fuel-fired furnaces when high temperature gases are discharged at a level higher than the furnace openings. This is commonly known as chimney effect. Slight negative pressure is required while operating the fired heater so that combustion products do not escape into the surrounding area through the furnace openings. If pressure is positive inside the furnace, when the opening the inspection window and the doors, hot flue gases will come out and hit your face, making inspection not possible. Shown in this figure is a natural dart furnace installed in a refinery. Look at the chimneys. There are several chimneys installed on the furnace for exhausting the flue gas. While negative pressure is desirable, too much negative pressure or draft will cause indirect harm by way of air leakage into the furnace through the furnace openings, referred to as tramp air. Tramp air cools the combustion gases and reduces the furnace efficiency. This leaked air has to be heated to the flue gas temperature before it leaves the furnace through the stack. This again wastes the energy and reduces furnace efficiency. Examples of furnace openings include leakage around burner mountings, observation or inspection ports, doors that were opened and closed frequently. Hence, correct draft is to be created and maintained by the system. Draft is measured in mm or inches of water column. Furnace pressure is typically measured using a differential pressure transmitter. Normal operating ranges are minus 0.5 to minus 1 inch of water column. The draft is maintained and controlled by a damper at the furnace stack, that is exit hood, as illustrated in the figure next. This figure illustrates a fired heater furnace with the internal arrangement. Observe the burner mounting and the inspection windows, as well as the damper control and the location of the draft cages. The draft control is illustrated in this sketch. A pressure transmitter senses the draft in the furnace, and its output is used by the draft controller to vary the damper position, which will regulate the flue gas exiting the furnace. Question number 12. What is the meaning of 1, 2 pause heat exchanger? Your time start now. Your time is up. The answer. The first number indicates the number of shells, and the second number indicates the number of tube passes. It means the given heat exchanger has one shell and two tube side passes. The number of tube passes is a design parameter and is usually adjusted to get the required tube side heat transfer coefficient. Illustrated in this figure is a 1-2 pause heat exchanger. Observe the pause partition plate. It provides two passes on the tube side. On the shell side, there is a single pass for the fluid. For a given heat exchanger, everything else remaining constant, when you increase the type of heat exchanger from 1-1 to 1-2 type, the tube count approximately become half for each pass. This will lead to doubling of the tube side fluid velocity and consequently higher tube side coefficient is obtained. Thus, the overall heat transfer coefficient U will also increase. So, for the same heat duty, this will lead to reduction of heat transfer area. The second most important reason for increasing tube passes is to have minimum velocity needed for process stream to avoid fouling. For instance, solids in the liquid, such as cooling water, will tend to settle down and deposit on the tubes if the velocity is below a certain value. The negative effect of increased velocity is higher pressure drop. Thus, increase in tube velocity is done keeping in mind the limit on the pressure drop specified for the design. Question number 13. A shallow tube heat exchanger is used for cooling a process stream. Water, the cooling medium, flows on the tube side. The cooling water flow through the tubes is increased such that the tube side velocity increases by 20%. The flow is turbulent. What will be the magnitude of increase in the tube side heat transfer coefficient? Your time starts now. Your time is up. The answer. For turbulent flow, the Dieter-Boelter equation is used for determining heat transfer coefficient. The heat transfer coefficient according to Dieter-Boelter equation is proportional to Reynolds number to the power 0.8, which is in turn proportional to the velocity to the power 0.8. The ratio of the new heat transfer coefficient and to the old heat transfer coefficient equals Re to the power 0.8 divided by Re1 to the power 0.8, which equals U2 to the power 0.8 divided by U1 to the power 0.8. So the ratio of H2 by H1 becomes 1.2 to the power 0.8. So H2 is H1 times 1.2 to the power 0.8. So the increase in heat transfer coefficient is 16%. Question number 14. In a heat exchanger, water is heated by condensing steam. Assuming that the steam is losing only the latent heat, draw a temperature profile for the same for a countercurrent flow. If you consider the heat exchange by parallel flow and cross flow for the same service, which will have the maximum LMTD for a given set of terminal temperature conditions. Your time starts now. Your time is up. The answer. This figure illustrates the temperature profile of a countercurrent condenser. Note that the steam is losing only the latent heat. Hence, the hot stream temperature profile is constant. That is, the TH in is equal to the TH out. This figure is a temperature profile for the parallel flow condenser. Since the terminal temperature conditions are the same and only the latent heat is removed, the LMTD will be the same for all the three types of flow. The LMTD written for countercurrent flow is presented below. Assume that steam is condensing at 150 degrees centigrade and the water is heated from 35 degrees centigrade to 75 degrees centigrade. For countercurrent heat exchanger, the LMTD is written as follows. LMTD equals 150 minus 75 minus 150 minus 35 divided by ln of 150 minus 75 divided by 150 minus 35, which equals 93.6 degrees centigrade. For countercurrent heat exchanger, the LMTD is written as follows. LMTD equals 150 minus 35 minus 150 minus 75 divided by ln of 150 minus 35 divided by 150 minus 75, which equals 93.6 degrees centigrade. For cross-flow heat exchanger, for the condensation, the correction factor F is taken as 1. So the LMTD equals 93.6 degrees centigrade. So we have seen for all the three types of flow, the LMTD is the same in this problem. Question number 15. You have two rods, one made of copper and the other made of aluminium. Thermal conductivities of copper and aluminium at 25 degrees centigrade in watts per meter degree centigrade are 401 and 237 respectively, and heat capacities of copper and aluminium at 25 degrees centigrade in joules per gram degree centigrade or 0.385 and 0.9 respectively. If one end of the two rods are kept at the same temperature, which one of them will transfer heat faster? Your time starts now. Your time is up. The answer. The answer is copper. The rate of heat transport in a metal is dependent on the conductivity of the material as per the Fourier law of heat conduction. This figure illustrates pictorially the placement of the two rods at the same higher temperature T1 and the heat conduction process. The rate of conductive heat transfer is faster in copper due to its higher thermal conductivity as expressed by the equation Q is equal to minus Ka T1 minus T2 divided by L. Heat conductivity is how efficiently the heat is transported from hot end to the cold end, whereas heat capacity is a measure of the amount of heat needed to rise the temperature. These two are different properties. In conduction, it is a thermal conductivity which is important. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.